This conference will now be recorded.
Hello everyone. The topics we are going to discuss today, different compounds of boron and aluminium. Probably we will not be able to reach aluminium, only boron compounds we will be able to discuss. Now this problem that you are seeing here, this is based on anomalous behavior of boron. That is, the boron is the first member of group 13 elements and its behavior is completely different from the other members like aluminium, gallium. Okay. So based on this anomalous behavior of boron, here we have this question which is saying that borons cannot form which one of the following anions. So here you can see total 4 different types of anions are there. The first one is BF6 3-. That means total 6 fluoride ions surrounding boron with 3 negative charges, and BH4-, BOH whole 4 single negative charge, and BO2-. Now with respect to negative charge, there is no issue because for F it is F-, for H it is H-, for hydroxide HO-, and for each oxygen it is 2 negative charge. So with respect to charge it is fine. But where is the problem? Based on which we have to choose the correct option, which is basically that anion that is whose formation is not possible. Okay. Now this is based on the coordination number of boron. Remember, boron, it is from second period. Then aluminium, it is third period. Then the next one, fourth period. Now only in second period, there is no d orbital, right? And as there is no d orbital, if we consider the valential electronic configuration of boron, it is like this. Boron, it has atomic number 5. So total 5 electrons will be there. Now if you consider the valence shell, just omit this part, it is not required. It is NH2NP6, that means it is 2s2 2p1. Total 3 electrons present in the valence shell. So when it is in ground state, then it is having 2s2, sorry, it is for the next one. It is having 2s2 2p1 configuration. Now when it is in excited state, this pair it will be broken, and that electron now it will be transferred to p orbital. So now it is in excited state. You can see total 3 electrons. So these 3 electrons can take part in bonding, and in this vacant orbital, if there is some anion which will provide electron solely from, that is the electron will come only from the anion, then this vacant orbital can be used. But important point is after 2p and 2s, there is no d orbital. So further there is no such orbital. But in case of aluminium or gallium, extra d orbitals. It is true that it is vacant, but still d orbitals are present. But here that is not possible. So only we are getting total 4 orbitals. So maximum coordination number 4. It cannot be more than that. Now if you consider here, if you look at the options, here these two coordination number 4 easily we can understand. And for BO2 also, that is per oxygen, it is basically valency 2. So 2 oxygen, it is basically equivalent to 4 coordination. So this is also okay. But BF6 3-. So here surrounding boron total 6 coordination, that is not possible. So that is why correct option will be the first option, BF6 3-. Boron cannot form this type of ion, so at 6 coordination number required, because maximum coordination number is 4, not more than that. This is the correct option. Next, we will start today's class with the topic some important compounds of boron and aluminium. In group 13, there is basically boron, aluminium, gallium, indium, thallium, but only these two we have in syllabus, that is some important compounds. So what are the important compounds? So when it is important compounds of boron, here we have borax, then we have boric acid, and we have diborane. And in case of aluminium, we will have AlCl3, and alum, its structure is little complicated. So we will just have a some primary idea about all these molecules. So this is basically borax, where 2 negative charges are there over boron, because total 4 coordination is there. So negative charge, and these 2 negative charge will be balanced by sodium. So actually the formula for borax is Na2B4O7, but here we can see only the anionic part. Then for boric acid, the structure is like this. It is H3BO3, or sometimes it is also written as BOH3. Both are fine. And diborane is B2H6, which is a dimer of, it is dimer of BH3, that is hydride. Now, in case of aluminium chloride is okay, it is simple, AlCl3, but when we consider alum, it has very large structure. It is basically salt, two salts are there. You can see here, potassium ion is there, sulfate, that means potassium ion, sulfate ion, and there is total 6 and 6, total 12 water molecules are there. We also, obviously, we will have Al3 plus. So there is Al3 plus, K plus, sulfate and water molecules. So this, there are actually different types of alum. This is one of these example, which is popular. Okay. So first we will start with boron compounds, borax, boric acid, diborane. We will see their preparation. If there is some unique structure related points, that also we have to consider. So preparation, properties and applications, and also if there is some unique features of structure that we have to know about all these three molecules, borax, boric acid, diborane. So we'll start with borax. Now look at the formula. It is Na2B4O7 10 water molecule. Now this molecule, it will be easier for you to understand its structure if you consider it as a derivative of tetraboric acid. Now what is tetraboric acid? Tetraboric acid is H2B4O7. As if these two hydrogens, if you replace with sodium, then it will be borax. So first, let's see what is tetraboric acid. So this is tetraboric acid, total 4 boron, that means B4. Hydrogen is 2 only in OH group, so it is H2, and total number of oxygen 1, 2, 3. Here also 1, 2, 3, 6, and this is number 7. So H2B4O7, that is tetraboric acid. And now when it is borax, the difference is, now in case of borax, you have this type of ion, and this form, there is a specific name which is known as prismatic form. Now it is not mere replacement of 2 hydrogen with sodium, there is also some negative charge and some extra oxygen there. So see, this is actually this ion, that is B4O5 OH whole for 2 minus. So if you look carefully, that is if you compare these two structure carefully, these two are actually same. Only the difference you can see in this part. In the previous structure, that is tetraboric acid, boron, there is total 3 bonds and it is not having any negative charge. But now if you consider this part surrounding boron, there are total 4 bonds and there is negative charge present over both. Right? Now these two negative charge, that will be satisfied by 2 positive charge which is coming from 2 sodium ion. So B4O5, that is 4 boron and 5 oxygen. These 5 oxygen are actually, let me change color. These are the 5 oxygen. I am marking with blue. And this 4 oxygen, that is the part of HO, that is basically present here. 1, 2, 3 and 4. And there are total 4 boron. So in this way you can understand this is the actual structure. If we consider this anion in this way, if we represent the formula, you will be able to understand this structure. But for simplicity, we express it in this way, that is Na2B4O7 10 water molecule. Fine. So the actual formula, it is like this, because B4O5 HO4, if you simply focus on this part, I am marking with violet, this is basically this ion. So these 2 negative charge balanced by sodium, and there is this extra water molecules, 8 water molecules. But when we represent it in this way, which is easier to understand as a derivative of H2B4O7, so in that case it will be 10 water molecules. If you count the atoms, it is actually same in both cases, whether you represent it in this way, that is Na2B4O5 OH whole 4, or you represent like Na2B4O7 10 watt. So mostly we'll see it is represented as Na2B4O7 10 water molecules, not like this. But this is the actual formula, right? Then there is another form which is known as Jeweller's borax, or because of its structure, it has the name octahedral borax. This is prismatic form, this is octahedral. Now, what is the difference? The difference is only in the number of water molecules. In borax, it is 10 water molecules with Na2B4O7 unit, and here it is 5 water molecules, which is known as Jeweller's borax. So basically, this molecule, it has some application in jewelry making processes. So that is why it has this type of name. Next, we'll see the preparation method of borax. How can we make this molecule starting from different substances? So the first one is from tinkle. Now, tinkle is nothing new. It is not a different substance. It is also actually borax, but it is naturally occurring borax, and it is also called suhaga. Now, tinkle obtained from dried up lakes contains 50% borax. So the tinkle that we are getting from dried up lakes, there is 50% amount of borax. So it is with impurity. We have to just remove the impurity, then only we can get pure borax. So for this purification, what we do, it is tinkle is boiled with water and then it is filtered to remove the insoluble impurities of the clay, sand, etc. So these are the impurities because they are insoluble, so we can do filtration process, and after filtration, the filtrate part, if we concentrate it, there is appearance of crystals of borax. So in this way, from tinkle, which is naturally occurring borax, we can prepare borax. Then the second method is from colemanite. So borax, it is actually ore of boron. We can make borax from this ore. We have to treat it with sodium carbonate, solution of sodium carbonate. So we are getting Na2B4O7. Remember, when we represent an equation, mostly we do not write the water molecules. It is only Na2B4O7. This part is written, not the water part. 10 water molecules not written. So we are getting borax, and we are also getting another boron compound, which is NaBO2. And calcium carbonate, as it is not having any solubility, it will remain in the PPT form. Now this PPT of calcium carbonate, we can remove it by filtration process. And after filtration of CaCO3, which will remain as residue. Now the filtered part, if we do concentration and cooled, then we can get the borax crystals. Now here, as I have mentioned, we are getting also another boron compound. Now from this boron compound also, we can make Na2B4O7. So nothing is wasted. That is the source of boron that we have used is Ca2B6O11, which is colemanite ore. And when we are treating it sodium carbonate, directly we are getting borax, but we are also getting another boron compound. And that compound also can be converted to Na2B4O7. How? So this NaBO2, which we call sodium metaborate, it is basically present in mother liquor. Only the PPT part is CaCO3, and in mother liquor there is both borax and NaBO2. But borax we will get in the form of crystal, and in the mother liquor there will be still NaBO2. Now this can be again converted to borax. We just have to pass a current of CO2 through it. Okay. So this carbon dioxide, it is making, that is, it is reacting with the sodium part of NaBO2, and it is now converted to Na2CO3, and see, we are getting borax again. So nothing is wasted. So this is the second method for the preparation of Na2B4O7. The third method is starting from boric acid or orthoboric acid. Now you can call it that is H3BO3, which is boric acid. You can also call it with orthoboric acid. Both the names you should know, because when you will actually get some problem, you will solve some problem. Sometimes it is mentioned as boric acid, sometimes orthoboric acid. So both the names should be known. Borax can be prepared in small amounts by neutral, that is in laboratory method if we consider. by neutralizing boric acid. So boric acid, as we are saying, it is acid. So it will react with sodium carbonate as if it is acid-base reaction. And we are getting Na2B4O7 along with water and carbon dioxide. So here also, when we are cooling the reaction mixture, there is crystals of borax we are getting, because if you look at the product side, CO2 is gas, so it will be removed easily. Only in the reaction mixture part we have water and our desired product. So easily we can get the crystals of borax. So this is the third method. After these preparation methods, total 3 preparation methods we have seen. One is from Tinkle, the second one is from Colemanito. The third one is starting from H3BO3, which is the source of boron here. Now the properties. Before going to properties, let's see. Crystals look like this, but if you make powder out of it, then it will be simply white powder. How it reacts with water? It is white crystalline solid. Water solubility, if we consider, cold water less soluble, hot water more soluble. Now the solution in hot water, it is alkaline in nature. Why it is so? It is because of the formation of NaOH. Now Na2B4O7, when you are reacting with water, there is basically formation of H3BO3. Now if you are thinking this is acid and this is base, then why it is still alkaline? It is because though we are saying H3BO3 acid, but it is not at all very strong acid, very weak. So with respect to the NaOH is very strong. So that is why ultimately the solution after reaction, it will be, that is the solution of Na2B4O7 in hot water, that will be alkaline, and this nature is because of the formation of sodium hydroxide. Okay, so as if nothing. So fine, it is the hydrolysis of borax we are getting, acid and base, but base is very strong, so that is why ultimately the solution is alkaline in nature. This is the first property, reaction with water. Now the second property is very important, which is action of heat. If you apply heat over borax, what happens, that we have to see. But application of this reaction we do find in borax bead test. Okay, so what happens when we heat borax? As you can see, there is total 10 molecules of water. So when you are heating it, first there is loss of water molecules of crystallization, and there will be a swelling, and it will be converted to puffy mass. So when we are first heating it, we are getting Na2B4O7 without 10 water molecules, and this is anhydrous sodium tetraborate. It is, you cannot say it is borax, it is anhydrous sodium tetraborate. It is white and opaque mass. Opaque means the opposite word of transparent. Okay, it is opaque. It is puffy mass. Now if you are further heating it, so this is the, suppose I am numbering it, this is A, this is B. So A is basically this one, this is B. So upon further heating, further you are increasing the temperature. Now Na2B4O7, it is converted to NaBO2, sodium metaborate, and boron trioxide, B2O3. Now this is called borax glass because its appearance is like a transparent glass-like bead. So the first appearance when you have started the heating process is puffy mass. Then you are again increasing the temperature. Now there will be some solidification process, and it will be converted to transparent glass-like bead, as you can see in this picture. Okay, so we have taken a wire. You can also use platinum wire. Just take some amount of borax and simply heat it. And when you are heating it, so as you can see, it is mentioned here, first there is puffy mass, then you will get this type of transparent glass. So if you observe carefully, you can see the steps. First there is formation of some opaque mass, and then it is converted to transparent glass-like material. Now this glassy bead is actually used in borax bead test. This is qualitative analysis. That means if you want to know there is some certain metal ions present in the sample or not. Suppose you are having some unknown sample of inorganic ions where these ions may be present, but you want to be sure, then you can do this test. So what you will do, once you have formed this type of glass-like bead, then you have to take this sample, that is, you have to touch this sample with this glass-like bead, and again we have to heat it. Now, depending on what metal ions are there will be different color formation, and from the color we can predict whether this particular metal ion is present or not. Now, it is not just for any metal ions. You can do this Borax bead test. There is obviously some specific ions, and mostly we'll see it is transition metals. As you can see here, nickel, all are from D block. Nickel 2 plus, cobalt 2 plus, chromium 3 plus, copper 2 plus. Okay. So the necessary condition is there must be some color formation, because if there is no color formation, you will not be able to understand which metal ion is actually present. Fine. So just for example, when you have already obtained this glass-like bead, which is this one, now you have some sample where cobalt salt is present. Now it may be any salt, suppose cobalt chloride or anything other ions are present. Okay. So this salt of cobalt, which is having +2 oxidation state, when you are heating it, then there is formation of COO. So suppose if you have taken cobalt sulfate, there is a gas formation, that is the sulfate part is removed in the form of sulfur dioxide or trioxide, and you are getting this oxide of cobalt after heating. Now this oxide of cobalt, it is ultimately reacting with this B2O3 part which is present in this transparent crystal, and it is forming cobalt metaborate, COBO2 whole 2. Fine. So it is having some blue color. So if you consider the picture, it is like this. So because of this particular blue color, if you take any other ion, there will be some different color. So from the color, actually, we can understand that what is present. Fine. That is which metal ion is actually present. Now here we will have a table where you can get all the informations. These are the metals. Basically, it will be ions. Copper 2 plus, Ap2 plus, Cr3 plus. And depending on whether you have taken oxidizing flame or reducing flame, in hot, whether it is in hot condition or cold condition, different types of colors may be there. So as you can see, when it is cobalt, as you have seen in the previous slide, it is basically blue. Whether it is reducing or oxidizing, whether it is hot or cold, always it is blue. Then suppose you are doing it for copper 2 plus, then you can see it is green and blue in hot and cold condition. So in this way, we can differentiate which metal ions are present. Now, based on this information, that is Borax bead test, let's solve this question. So the question is saying that the Borax bead test is responded by divalent metals, heavy metals, light metals, metals which form colored metaborate. Just have a look in the previous slide. What we have seen here, we have formation of cobalt metaborate, COBO2 whole 2. Remember sodium metaborate, we have NaBO2, we have already seen in the during the preparation method, right? I just want to show you. See here we have this NaBO2. So NaBO2 means Na plus BO2 minus. It is having single negative charge. So when it is cobalt 2 plus, obviously the formula will be COBO2 whole 2. Okay. So this type of color formation is important. It is not that whether you are using any divalent metal or trivalent metal, because when it is chromium, it will be trivalent. When it is copper, it is divalent. So it is not dependent on the oxidation state. Fine. And also it has nothing to do with heavy metals or light metals. And these metals, as you can see here, we cannot say these are heavy metals, right? And so it has nothing to do with heavy or light, but the only necessary condition is that there should be some color formation, and the color is because of different types of metaborate salts of metal ions. So that is why the last option, that will be the correct option. Borax bead test will be that is, it will be positive, or we can say it is responding. It is only for those metals which can form colored metaborate. Because if it is not forming any color, the glass bead, it will be still like transparent, and there is no difference once you have touched with the metal sample. then it will not work for us. Okay, so the last option is the correct option. So after Borax big test, the third property, how they react, how it reacts with acids. So reaction with acid, we will see first how it reacts with hydrochloric acid, and the second H2SO4, mineral acid, both the acids as you can see here. So Borax reacts with acid, whether it is HCl or H2SO4. In both cases, we are getting boric acid. And the byproduct is obviously different. It is sodium chloride because you have taken hydrochloric acid. In the second case, it is sodium sulfate because you have taken sulfuric acid. But important point is you are getting boric acid. So this process, that is this reaction that we are discussing under the properties heading of borax, it can also be as if the preparation method of H3BO3, isn't it? Because when you are treating borax as a source of boron, you are treating it with solution of HCl, aqueous solution of HCl or H2SO, you are getting boric acid. So remember, in the next compound we are going to discuss after finishing borax is H3BO3. So there we can see that this equation can be used as a preparation methods for H3BO3. Next, how it reacts with alkali. So reaction with alkali, that is NaOH, sodium metaborate is formed along with water. Reaction with ammonium chloride. So with ammonium chloride, it forms this compound you are seeing first. It is called boron nitride. Not just boron nitride, although here only this one is mentioned because this is only boron specific compound where nitrogen is also present, and the source of nitrogen is basically NH4Cl. And here we are discussing the reaction with NH4Cl. So this is the main compound because boron, the source is Na2B4O7, and nitrogen, the source is ammonium chloride, NH4Cl. And the byproducts are another boron compound is also there, which is B2O3 and sodium chloride water. And Bn, though details of this molecule structure is not in syllabus, but still if you want to know, it has this type of structure, though it is not the only structure, it can remain in different forms, but mostly we represent this form when we are considering its structure. Okay, this is not a single molecule. It like this, the representation of the structure is like this. So I'm talking about boron nitride. So here we have a question. See, one reaction is mentioned. Borax, how it is reacting with water. And one of the product is mentioned, which is NaOH. It is asking what is the other compound which is written as A. Now Na2B4O7 under the properties heading of borax, we have discussed one reaction, that how it reacts with water. So there you will find this equation that Na2B4O7 reacts with water, it forms some alkaline solution, and this alkaline solution is because of NaOH, because H3BO3, though it is acid, but it is very weak. So ultimately NaOH is overcoming whether ultimately the solution will be acidic or alkaline. So it is alkaline, but this is actually the compound A, and this is boric acid, which is also known as orthoboric acid. So correct option should be this one, but here you can see some other options are also mentioned. So metaboric acid, it is HbO2, it is not correct, and pyroboric acid, that is basically H2B4O7, and tetraboric acid, that is also that is pyroboric acid is also called in this way. So these are different formulas, right? HbO2 metaboric acid, orthoboric acid is only H3BO3. So this is the correct option. On addition of mineral acid to an aqueous solution of borax, the following compound is formed. Remember how borax reacts with acid. Two examples we have seen. One is HCl, which is mineral acid. Another one is H2SO4, that is also mineral acid. So when it is reacting with mineral acid, we will just have a look in the previous slide. So this is the reaction. So what we are getting, this is the common compound we are getting, whether you have taken HCl or H2SO4, which is H3BO3, that is orthoboric acid. So look at the options. Orthoboric acid is present here, so this should be the correct option. Boron hydride is BH3, which remains in the dimeric form B2H6, so this is not correct. Then metaboric acid HbO2, this is not formed. Pyraboric acid, we have already seen the formula H2B4O7, that is also not correct. Fine. So correct option, second one, orthoboric acid or boric acid. Both are used for the same compound, which is H3. Now the application part, there is nothing much to discuss. We'll just have a quick brush up. As a precursor to several commercially important compounds of boron. So from borax, you can also make other compounds. For example, you can make H3BO3. So that is why it can be used as a precursor. Then the very important application is in manufacture of enamels and glazes for earthenware, because when it is glazed, it becomes resistant to heat, stain, scratches. So that is the purpose of glazing, which is done with this compound. As a flux in soldering, soldering is joining metal parts, and preparation of some medicine also, because it has some antiseptic properties. Now this is very unique property. Then in cosmetics, then heat resistant borosilicate glass, different type of glass making also it has application. Now there is a compound called paraxoborate, which is important cleansing and bleaching agent present in washing powder. Now to make that compound also, borax can be used as boron source. Borax bead test, we have already seen the application, which is application in laboratory for qualitative analysis of some specific metals and in softening of water. The next compound is boric acid, which is also known as orthoboric acid. Now another name you should know is it is also called hydrogen borate, because see, if you look at its formula, it is like this. That is structure, not formula. If you simply remove the hydrogens, it will be, sorry, I have wrongly drawn 4 bonds. It is only 3. A BOH whole 3, or you can write it as H3BO3. So here if you simply leave the 3 hydrogen atoms, it will be BO3 3 minus, which is basically borate ion. But as we have hydrogen, so that is why the name is hydrogen borate. This compound is white crystalline solid, and if you touch it, there is a soapy type of feeling. Now why we have this type of soapy feeling, we will also know that in the overall molecular geometry of this acid is trigonal planar, which is clear from the structure as I have drawn. So here the boron, the central atom, and all the 3 OH groups all are in the same plane. So it is trigonal planar. With respect to B, if you consider the geometry, it is trigonal planar. Boron is occupying the central position and linked to 3 OH groups. But they do not remain in this single molecule form. There is actually some layer type of structure, which is 2-dimensional layer type of structure, in which planar BO3 3 minus units, which is basically the borate units. So all the borate units of several H3BO3, they are joined by hydrogen bonds. So as you can see here, if you simply focus on the solid bond part, just focus on this part, it is with solid bond, there is no dotted. So this is one H3BO3, then another H3BO3, third H3BO3. Now all these BO3, H3BO3 units, this is one H3BO3, this is second one, all are joined by some dotted pink colored line, as you can see here, and these lines are nothing but hydrogen bond, where the oxygen of one H3BO3 molecule is making hydrogen bond with the hydrogen atom of the another H3BO3 molecule. So this is basically 2-dimensional structure, as if it is on the plane. But if several this type of plane, if you consider stacking over one another, then you can understand how it is having different layers one by one. That is, if you imagine it from three-dimensional point of view, it will have some layer structure. So these BO3 units, they are joined by hydrogen bonds. So BO3 unit means this part. So this is one BO3 unit. This is another BO3 unit. Okay. So the adjacent layers in the crystals of boric acid are held together by weak forces of attraction. So this is just one layer. If you have another layer, then two layers. Between these two layers, there is weak force of attraction. Okay. And the distance between these two successive layers, 318 picometer. And because of these weak forces of attraction, one layer can slide over another. And that is the reason why when we touch it, there is some soapy type of feeling, because it is slippery. One layer can easily slip over another. So it is having some soft nature because the interaction of two layers is not very strong. And the layers can slide over each other. And we can have soapy type of nature. So this is the points, different unique points related to the structure of H3BO3. Preparation method of H3BO3. See, this reaction Na2B4O7 reacting with HCl, reacting with H2. These two reactions you have already seen under the under the properties heading of borax. Now, the properties of borax, the same reaction we are now discussing under the heading of preparation method of H3BO3. Here the starting material is borax. So hot concentrated solution of borax to HCl or H2SO4. The resulting solution on concentration and cooling, you get the desired product, which is H3BO3. Now from colemanite also you can make it. Remember, in borax we have used colemanite for preparation of borax. Now also for preparation of H3BO3 you can use this ore, but now we are using different, the other reagents are obviously different. So first the mineral is powder mixed with boiling water, and then sulfur dioxide gas is passed through the mixture. The resulting solution on concentration and cooling, it gives crystals of boric acid. And here the other byproduct that is formed, calcium bisulfite, HSO3, which is bisulfite, and it is having high solubility in water, so it will not create any problem. It will simply remain in mother liquor, and you can easily get the crystals. You can do the filtration to get ultimately H3BO3. The third method, it is not a single reaction. The third method in general, you can say, by doing hydrolysis of different types of boron compounds. Each cases you can get H3BO3. So what compounds we are using? We have used BCl3, boron trichloride. You are doing hydrolysis, that is reaction with water, you are getting H3BO3. HCl is byproduct. Then you can start with diborane, which is a dimer of BH3. Basically, after finishing H3BO3, the next compound we are going to discuss is this one, B2H6. Okay. So B2H6 you can use for preparation of H3BO3 by doing hydrolysis. Here the byproduct is hydrogen gas and boron nitride. Remember, we have already seen this molecule. This also, when reacts with water, there is formation of H3BO3 and byproduct is ammonia. So we have used here halide, hydride, and nitrite, these three compounds of boron. After preparation, properties. The acid is sparingly soluble in water, but highly soluble in hot water. Fine. Action of heat. Boric acid, when we are heating it at 373 Kelvin. Okay. 273, it is 0, so it is around 100 degrees centigrade. So first there is formation of HbO2. And then when we are increasing the temperature to 413 Kelvin, we are getting tetraboric acid, which is H2B4O7. Now, if you are doing further heating, that is, if again you are heating this tetraboric acid at red hot, which is greater than very high temperature, greater than 450 degrees centigrade. That means in Kelvin it is just more than 600, right? It gives boric anhydride, that is B2O3. Now this B2O3, it is, remember, it has some glassy type of appearance. So first heating, you are getting metaboric acid, this one. Then the second heating at 413, this is 373. And this is red hot, very high temperature. Ultimately, you are getting B2O3, fine. Then reaction with ammonia, fusion of H3BO3 or BOH3 in an atmosphere of ammonia. Temperature is very high, we get boron nitrate. And remember, this is the reverse reaction of preparation of H3BO3 starting from Bn. In the previous slide, we have seen when Bn is, we are doing hydrolysis, we are getting H3BO3 along with ammonia. Now, as if we are doing the reverse reaction. Now, the fourth point under properties, this is very interesting. So, when we look at the formula H3BO3, it seems as if it can donate proton like H plus, right? As if it is behaving as Bronsted acid, but actually it is not so. Though it has a formula like H3BO3, but remember there is no such H plus generation. So it is not Bronsted acid. It is Lewis acid of boron, but it is monobasic. But why we are saying it is monobasic? Because we are saying it is Lewis acid. Now Lewis acid means any molecule which can accept lone pair of electron from some other species. That is, it can accept negative charge. Then why we are saying monobasic? So once we see the equation, it will be clear. Now first, I try to understand why it is Lewis acid. It is Lewis acid because if you consider total number of electrons surrounding boron, boron has total 3 valence electron and it is using this 3 valence electron for bond formation with oxygen. And oxygen, it is also sharing its 1 electron, but surrounding boron there is total 6 electrons. So it is electron deficient, octet is not complete, and that is why it behaves as a Lewis acid. Now when it is reacting with water, in water, as if it will accept the HO part of water. If you write water like this, HOH, so it will take the OH part of water as if it is taking the negative charge because it is behaving as Lewis acid. And when it is taking the HO part of water, this part is removed in the form of H plus. So as if there is a release of proton from the water molecule. But remember, this proton is coming from water, not from H3BO3. So that is why you cannot say it is Bronsted acid. But it will behave as a monobasic acid because ultimately in the reaction medium there is a generation of proton. So the equation is like this. Here we have this molecule of H3BO3. It is reacting with water, so I will write water in this way. Now this OH part is taken by this boron, and now surrounding boron there is total 4 H. But this extra negative charge is present because extra HO minus it has taken from water. So the other part of water that will be removed in the form of proton. So ultimately in the reaction medium there is H plus, but the source of H plus is not H3BO3, it is coming from water. So water is here as if donating this HO and water is giving the proton. So you cannot say here H3BO3 is the Bronsted acid, it is not correct. But ultimately we are getting H plus, so that is why we are calling it monobasic. Now this equation you can also write in this way. See, now we have written 2 water molecules. But in this equation, there is only 1 water molecule. So when there is 2 water molecule, 1 extra water molecule, it can combine with this and ultimately it can form hydronium ion. Now look at this equation, how it is written. H3BO3 plus 2 water molecule. This is BOH whole 4 negative, which is same as this. And there is hydronium ion. So when you are writing 2 water molecule, you have to write hydronium. But if you are writing 1 water molecule, you have to write simply H plus. So based on this acidic nature problem is very common. So be very careful. that it is Lewis acid, it is more behaving in a monobasic way, but it is not Bronsted acid because it is not giving any H plus directly. It reacts with NaOH because of its weak acidic nature, and it forms sodium metaborate. And also depending on these different, that is when it is 1:1, we are getting this type of reaction. When we have taken in this ratio, now the product is different. So 1:1, the product is NaBO2, sodium metaborate. But with this ratio, it is Na2B4O7. Fine. The next property is formation of boron trifluoride. Boron trifluoride can be generated from H3BO3 when you are treating it with CaF2, which is basically the source of fluoride ion, and also acidic medium is required, concentrated sulfuric acid, you are getting BF3 along with calcium sulfate. Reaction with soda ash, which is nothing but Na2CO3, in S block chapter we have seen it. So when it is heated with Na2CO3, there is formation of borax. Fine. Then reaction with ethanol, that is C2H5OH. Same type of reaction you can also get from ethanol. So boric acid or borate salt. So not just boric acid. Boric acid is H2BO3, but borate salt is when simply remove the H, it is only BO3 3- unit. So boric acid or borate salt, both when you heat it with ethanol in presence of concentrated sulfuric acid, there is a formation of ester, that is trialkyl borate. So as if there is OH unit, but now this, instead of this OH unit, we will have OET unit. So it is written as BOET whole 3 plus water. Now the vapor of this ester, triethyl borate, it burns with green edged flame like this. It is liquid, it burns, its vapor burns with green edged flame, and because of this specific color generation with its vapor, it can be used as a detection method. Detection of what? Detection of either boric acid or borate, because from both, whether you take the anionic form or directly the acid, in both cases there is formation of triethyl borate, which is a kind of ester, and it can be used as qualitative analysis. Qualitative analysis means we will be able to know whether it is present or not, not its amount, simply whether it is present or not. Okay. So related to this, we have a question here. Sorry, it is boric acid. A mixture of boric acid with ethyl alcohol burns with green edged flame, and that is because of formation of, it is ethyl borate. Remember, BOET whole 3. If you have taken methanol, then it will be ethyl borate, but we have taken ethanol, so it is ethyl borate. This is the correct option, not ethyl borax or methyl borax. There is no such terminologies. Now its application part. Uses of boric acid, manufacture of heat resistant borosilicate glass. So just like Na2B4O7, here also we have some, that is, it has used in different types of glass making. Then enamels pigments as a preservative, milk and food stuff. It is also having some mild antiseptic property as eye wash, and its lotion, that is aqueous solution of H3BO3, it is known as boric lotion, which has antiseptic, a mild antiseptic, not major antiseptic property. In some nuclear power plants as neutron poison, because it has the capacity to absorb neutron. That is, it is called neutron poison. In the treatment or prevention of boron deficiencies in plants also, H3BO3 can be used. Fine. So related to structure, we have this problem. Boric acid has trigonal structure. That is the first option. Then the second one is saying it has tetrahedral structure. Then it is saying layer structure in which BO3 units are linked by oxygen. It is true there is BO3 units linked, but that is not linked by oxygen. Just read the next one. Same information, only extra is planar BO3, which is true, and linked by hydrogen, not oxygen. So first option, it is not, that is completely we cannot say it is not correct, but D, it is single choice answer, so you cannot choose both of them. A is fine, it is trigonal structure, but that is also only if you consider from the point of view of boron, then this part is trigonal planar. But there is better option than A. Though it is not completely incorrect, but still compared to A, we have better answer, which is the last one, because it is only saying that it is linked by hydrogen bond. See, these are hydrogen bond. It is not linked by oxygen. It is true that that in hydrogen bond formation there is some link with oxygen, but we shouldn't say it in this way. It should be considered as, because it is this type of bond is hydrogen bond, so better we say it in this way that they are linked by hydrogen bond. So that is why the last one, the last option, that will be the correct option. Okay. Hot and concentrated solution of borax, Na2B4O7. Hot and concentrated solution, that is water solution. You are treating it with HCl. There is formation of A, there is formation of B. Now among A and B, B when heated strongly, there is dehydration. And after dehydration of B, we are getting C. So if we write this equation as if Na2B4O7, you are treating it with HCl, there will be also water, but we will just write it simply. There is A, there is B. Now when you are heating B strongly, there is formation of C. Now you have to identify what is this C. Now look at the option. It is saying that it is acidic oxide, basic oxide, amphoteric oxide, salt of a strong acid and strong base. Now this cannot be at all correct. Where it is true there is strong acid, but there is no strong base formation. Okay. And this reaction between HCl and Na2B4O7, remember when borax reacts with mineral acid, whether you have HCl as mineral acid or H2SO4, in both cases there is one common product, which is H3BO3. That means among A and B, one compound may be H3BO3. And when H3BO3 is heated, what is the action of heat on H3BO3? That we have just seen, we have just learned 2 to 3 slides before. So when it is heated, though depending on what type of heating you are doing it 373 or 413 Kelvin, or you are doing it at red heat, depending on that, there is different types of compounds. Okay. But here it is specifically mentioned that when you are heating B, this C is, we have already cancelled it, C is some oxide. So remember in which case there is formation of oxide when you are heating it. Remember all the equations. This is the first equation. When you are heating borax, there is formation of A and B. Now this B, when you are, if you directly write this equation, these are the equations. Gradually we are doing the heat. First it is 100 degrees centigrade, that is 373, then 160, which is around 413 Kelvin, then red hot. So gradually we are increasing the temperature. First there is metaboric acid, then tetraboric acid, finally there is boric anhydride, which is mentioned in a single equation like this, the directly strong heating. But if you are thinking that B, strong heating, okay, it is already mentioned strong heating, so you can directly go for it. And even if it is not mentioned at strong heating, suppose simply written heating, then also see, this cannot be answered because this is not oxide, this is acid. This is also not oxide, this is acid. Only in the last step, strong heating, you are getting this oxide. And B2O3, it is acidic oxide, that you already know because it is non-metal. And when you have some oxide of non-metal, it is obviously acidic. Basic oxide is metal oxide, and in some cases there is amphoteric oxide, okay, like Al2O3. But the first element of group 13, boron, its oxide is acidic. Okay, so that is why correct option will be option A. So this question is very important because you can have application of so many concepts. First of all, you have to know this reaction, how Na2B4O7 reacts with mineral acid. And in this reaction, there is formation of two products. Suppose if you have chosen NaCl, heating of NaCl, there is no such oxide formation because there is no oxygen in NaCl. So obviously you have to consider the other one, H3BO3. And when you are heating H3BO3, there is different types of compound generation. But as it has already mentioned strong heating, so obviously you can choose B2O3. Even if it is not mentioned as strong heating, simply heating is mentioned, then also it will be B2O3 only because these two are not oxide. These are acid. Fine. So we'll end the session here. Next day we'll start the third compound of boron, which is diborane. So up to this slide, we have finished the first two compounds of boron, borax and H3BO3. We are ending the session here. Thank you for listening.